Good morning, everyone. We will get started with looking at how embedded software development really happens. What are the tools that we use, and take a quick look at how it is different from what we do normally on a desktop. And this is a couple of slides. After there will be a demonstration of a typical IDE that is used in the embedded software development. So subjective. So we'll look at quickly software development and for an embedded system, typical flow, and then with a real IDE there will be a demonstration. Okay. So the reason we want to spend a couple of minutes explaining this is many of you are familiar with how a general purpose computer system works, and you are all familiar with writing code and then compiling code and running it on the same system. Say, suppose you are using Windows, you probably have Visual Studio IDE on the Windows system. You actually open the IDE, you type code there, and you say compile, then run. So the compilation in that case produces binary code for the processor on which your Windows is running. Assume you are running on a x86 based platform. The compiler in that case generates the binary code which can be run by the x86 processor. As we saw earlier, the binary code is different for different processor architectures, right? So if I generate code for x86, it runs with that. Again, there are also other things along with that. Normally, when you want to run a C program on a x86 based operating system like Windows or Linux, there are standard set of libraries that go along with that. So normally when you compile on a system like Windows or Linux, the compiler, the toolchain automatically links whatever is required. Some standard libraries get linked. Like for example, you are trying to do you write for take an example of say a printf routine, right? So you don't think about it when you write in C code, you write printf, and you run the program on your Windows machine itself. The printf comes on the console. But beneath that, there is a lot of standard libraries which get linked. So when your code actually is calling printf, probably a lot of operating system services are getting used, using which only you are able to see the display on your screen on the black command.com prompt window. If you open and you run the program there, you see the say hello world or whatever, right? But for that to happen, there's a lot of things which are automatically linked to your C program. You're only writing the printf function. The standard C library implementation for printf would have actually been written, by the compiler tool vendor. They would have given you all the standard libraries, and it knows how to use the Windows. Windows is an operating system. The screen is in control of the operating system. For that message to come on the screen, the library will make use of the standard services that the operating system provides, and then make sure that whatever message you're trying to print appears on the screen there. So all this automatically happens, and as a developer at a high level, we don't even think about all. We only understand, okay, how to use printf, call printf, the display comes on the screen, right? So any other function that you use, all the operating system, everything gets linked automatically. Now, when you talk about embedded system, right, there are two things. One is the embedded systems, as we saw earlier, are like small devices, right? They have very little memory. Many of them are they don't have your great user interface. So which means to develop code to run on that embedded system, you probably need another machine. Normally, very few embedded systems will probably have a compiler running on the same system because we saw resources are constrained. We only have a processor which is just enough for the functionality probably. Memory is also limited. Compilers and all really need a lot of memory and disk space to run because it's a very intensive computation. It needs a lot of memory to expand the code you written, do the code generation and all that. So typically, in an embedded system flow, as this this slide shows you, you typically have two things. One is called the development host, which is where you actually do all the development, and the target system. Target system is nothing but our embedded system, which may be running ARM or x86 or MIPS, or it could be any processor that we choose. Based on the processor that you are choosing, on the development host can be a Windows machine, could be Linux machine, could be a Macintosh, Mac OS, could be any standard platform for which the tool chain is available. Like if you want to develop for say ARM, there are a few vendors who provide what you call as the integrated development environment. IDE stands for integrated development environment. They provide a standard IDE for the ARM platform. And typically that IDE will support various ARM generations, right? You have ARM 7, ARM 9, maybe more variants have come in the recent past, Cortex. I mean, there are so many different ARM varieties itself because the ISA itself is different. ARM 7 uses a different ISA, ARM 9 uses a slightly different ISA. ISA is nothing but instruction set architecture. So ultimately, you need a compiler. If I assume my embedded system is based on ARM. Now, to generate code that will run on that ARM platform, I need a toolchain which will output ARM assembly language or ARM binary code actually. Maybe if it's ARM 7, I have to select ARM 7. If it's ARM 9, I have to select ARM 9. Or if I'm developing on say RISC-V, I need a toolchain which will generate the binary which a RISC-V code can understand. Similarly, it can even be even x86 is used in embedded systems. If it is x86, I need a toolchain which will develop it. Now this toolchain is what is running on the development host, which you see on the left-hand side. This block here. So this is the development platform where all your compiler toolchain, everything is running, and you kind of install whatever is needed. So you see this cross compiler, right? This word called cross compiler. What is the meaning of cross compilation? See, the development host probably is a Windows machine, for example, right? Windows machine is running on an x86 processor. So your tool chain, your compiler is running on it. See, the compiler code, compiler is also a program, right? The compiler is a program. Somebody wrote that code, compile it, you get the binary of the compiler. The binary of the compiler is in x86 because it has to run on the Windows machine. But when it, now you have selected the target as ARM, right? Now this compiler, when it runs, the code it outputs, which is going to be running on the embedded system, is going to be ARM binary. So the reason it is called cross compilation is because your development environment is x86, but you are generating code for ARM. So the reason, that is why the word cross comes in here. Normally if the compiler is generating code for the same platform, we don't call it as cross compilation. In this case, we call it cross compilation because the development host has a different processor architecture, whereas the target is a different processor. That's the word, the cross compile. So basically, as we saw in last session also, compilers, the front end of the compiler is the standard because they just try to understand the code you have written, parse it, lexical analysis, parsing and all that. Finally, the code generation, you have to choose. So in this case, if it's a cross compilation kind of a setup, it's going to choose the output, which is not the native on where the compiler is running, but it's going to output for a different architecture. And most tool chains, like if you take an ARM tool chain, there will be options to select. You want to generate for ARM 7 or ARM 9 or whatever, and so on. And so basically, you cross compile it, and then you'll have to have a way to now transfer it to the target system, right? Normally, the IDEs for embedded systems will come with some interface for downloading to the target. Maybe there may be a RS-232 port or a USB based probe. So there'll be some small piece of hardware which connects to some port on the embedded system, maybe through USB, or sometimes there's a specialized set of pins to which this attaches. It depends on the embedded system target you have chosen and the type of interface you have chosen. There are multiple varieties there. But all you can understand at this stage is there is a way by which this development system is connected to the embedded board. Okay, so it may be through a USB cable, it could be a specialized cable which goes and plugs into a special socket on the board. There are multiple options possible, but that is there. Once the compilation is done, there will be a small piece of code, typically something called as a boot ROM or something running on the embedded system, which has a way to receive the new binary and store it into flash or store it into RAM. Again, multiple choices are possible. Once you cross compile, there are no errors. The development, this IDE will produce a binary. Okay, and there are different formats for that. Maybe when you actually try doing it, you look at all the formats. The way that output is stored, right? It can be stored as something called S records. So there are multiple formats, basically, but it's ultimately it is binary code which has to get transmitted to the embedded system. So depending on your target system's capability, what it supports, you'll have to choose the right format on the development host, save it in that format, and then there will be some options to connect to the target and then transmit or download it to the target system. Where the target system, there may be a small boot ROM or there could be a specialized some JTAG based probe, but there will be some mechanism which the hardware supports by which you can push this code onto the target system, right? You can possibly make this code get flashed into the flash memory of the target system. That's one option. Or if you don't want to keep writing to the flash, some systems may provide you to, if they have enough RAM or whatever, you can actually push it into some portion of the RAM to which you have compiled, and then the system can run. Okay. Now here there are a lot of things which there are a lot more details. I'm not going into that, but what you have to understand is normally on a high end, if you're compiling on Windows or whatever, right? The code which is generated, typically they will use things like virtual address. Like for example, if you're running on Linux or Windows, the compiler, the linker, after the compilation, there's something called as a linker. The linker is the one which decides what address this code is going to be stored. Like for example, I have 10 variables in my C program, right? Variables need some space to be stored. So each space means you need a memory address, right? So in a high-end operating system like Linux or Windows which support virtual memory, all the programs are compiled and linked to use some virtual addresses. But when the program runs, the OS will take care of assigning physical addresses for that, and the translation is set up. Whereas when you are compiling for an embedded platform, the program has to be aware of what addresses I should link to. Because on an embedded system, we saw the other day, right, that RA4M1 has only some 32 KB of flash memory or something. And that memory may be at a particular address in the processor address space. What is a processor address space? A processor address space is nothing but, maybe I'll just quickly explain a few concepts because it's good to understand those concepts when you compile for, embedded system. See, assume, let's say our processor is say a 32-bit address, right? Okay, which means it's capable of addressing starting from say address 0. In topmost addresses, you can say 0xFFFF. So this is nothing but all ones, right? That's the biggest address you can have. Okay, I mean, assuming the processor is capable of addressing the whole thing, but in reality, that is the address space. But it supports flash memory. We said 32K of flash memory, right? The processor manual will say the flash memory is always available at, because it's all on the chip. If you took that Renaissance example, right? it's an on-chip flash. So the system designer, the hardware designer have fixed the flash to be at a particular address. Let's say it was designed to be at this address, 80001000 something. I'm just taking an example. And from here, 32 kilobytes. So maybe there's some address, the end address. So when your program is now compiled and linked, right, for the program to run properly, the variables have, assume you have some variables which need say 1K of space. Okay, you'll have to make sure when you set up the IDE, there will be things called linker definition files or configuration. So you'll have to tell, store all my variables and say this address. May say this address is, let us say for simplicity, I'm just taking it as say 1800, something like that, right? This is the start address of this 1 KB chunk. So I'll have to tell the linker, assign space for all the variables in this range. And for code, I can say it starts from here, maybe 10 kilobytes of space, use it for the code, right? So what will happen when the binary code is generated? Suppose in C program, let's take an example, right? Just to make sure you understand this is important concept to understand. Let's say I have a variable called int val. It's a global variable I have. I have my main program. Here I am having some variable, say int x, and I'm writing a statement called x equal to val. Okay. And there will also be some space where stack will be there. Assume that is probably part of the SRAM because we need read-write memory for stack. So this is a flash range. This is your SRAM. Say, let's say SRAM is at this address, just for, I'm taking an arbitrary number here, okay? SRAM is at a different address. Okay, now we can say the stack has to be given space here. This is going to be your stack area because any local variables will be on the stack, okay? And global variables, you can say I want to keep it again in some part of, I'm giving some space here in SRAM or whatever. I'm going to keep it here. Let's say this is going to be my dynamic global variables here, all the global. And here I can put some constants. In the flash, I can put things like constants. For example, here if I had defined in C, something saying const phi equal to 3.14 or something like that, right? All the constants which don't change, I could have configured and make sure they go into the flash itself because I'm not going to read and write. Okay, you can keep it in the flash, nothing wrong. Ultimately, what happens is, say this is a statement here, right? X equal to val. Okay, this will get translated into some assembly instructions, right? It may read some, it has to read some memory address, and it has to read some. I lost what I had. So okay, don't worry. So you got the concept, right? Let's assume, I'm not going to draw that again. Let's say we have SRAM starting at address 0x something, so 7F000000. Okay. And the code is at say some address. Code flash is at this address 0x800000. Okay. The reason this is important is when the assembly is generated, let's assume you have a function. Say let's say we had main. Okay. And assume we had one more function called F1. So each is going to occupy some amount of space in the memory, right? Assume from this main, I'm going to call this function F1. Okay. So in assembly, it will translate into a instruction called call, and there will be an address. Okay. So we understand this is all part of the code. Okay. If you look at it in the binary case, right? Call may be having some opcode, say 782 or something like that, right? And after that, the next 2 bytes in your code will be this address. Say, let's say I'm calling this address 1, right? So assume it's a 32-bit address. It may take some 4 bytes, like address 0 to 3, right? Assume this is a 32-bit address. I need 4 bytes to store this address. Are you understanding? So basically, this is nothing but part of your code actually, which is part of your binary file, right? Now, if your code is going to be placed in say this flash memory, right? Flash is here, right? So compiler will know main starts at say 8000, and after say main takes some 100 bytes or whatever, right? In hex. So F1 is going to be at some address, say 0100, for example. Okay, what has to happen? This address here should be 0x80100. So which means when the compiler generates code, I'm just trying to explain why you need to specify things, right? When I'm generating code in this case, the address of function F1, which is going to be kept in flash memory, that address has to be generated as part of your target binary. Are you getting the point? Because if you're making a call to a function, call is nothing but a subroutine call in assembly, which means it jumps to a particular location, executes and comes back, right? To jump to a particular address, I need to know where to jump. And in the C program, I'm making a function call, and functions are now going to be placed in the flash memory. So that address has to be inserted into the binary. Okay, only then the program will run properly. And this whole, similarly, if there's a variable reference, when that variable is being accessed, right? there might have been a instruction something like this, right? Move to accumulator some address. This is the address of val variable, right? So this address of val variable, if I am saying it is going to be in this SRAM region, the compiler, the linker should make sure this is placed in this region. Are you getting the point? Okay, this is the reason in an embedded development environment, you have to be aware of how your hardware architecture is. You should know on my board, this is where the code is going to be placed. This is the address ranges in the board. This is where SRAM is there. This is where flash is there. And you typically in the IDE, you will have to go and configure saying, okay, I want the code to be placed in this region of memory. I want the data section to be here, constants to be placed somewhere, and so on. There will be many, the stack is going to be here. So once you configure all that, the compiler will generate that binary with all the right addresses in place, so that when you push it to the target through using the USB interface or whatever, right, the code is now in proper form to run on the target. Is that clear? When you're doing development on Linux or whatever, we don't worry so much because Linux or Windows, they automatically assume the entire virtual memory address space of 4 GB to be available for every program. Okay, so they will just use virtual addresses. After that, it is the job of the operating system, like Windows or Linux, when the C program runs, the operating system will keep allocating memory. And there is a virtual to physical mapping which is run at runtime. So it is much easier for the compiler because the linker will just assume 0 to FFFF. That's my entire range, which is the entire virtual address range for say 32-bit processor, and it will generate code using the virtual addresses. After that, the operating system will take care. Whereas in our case, in an embedded platform, especially where you're not using Linux kind of a thing, where you're writing code and you're pushing it to the target hardware, you have to be aware of the address ranges. That is why it is important to read the data sheet of your microcontroller, understand where is the flash memory, where is the RAM, which address. It will be all given in the data. If you look at the data sheet, you will be able to see a diagram like what I showed, right? It will show where what register is available, where RAM is going to be there, where flash is going to be there, where boot ROM is going to be there. So all that information is there. So as a developer, you have to understand that and go configure your IDE. Once configuration is done, it's quite simple. It's like once the configuration is done, the code is going to get generated. The cross compiler, we are just showing the cross compiler. After that, there's a process called linking. Linking is where all these addresses are patched. Linking is the process of giving fixed addresses for every variable, every function based on your target architecture, and then you push it to the system. Then you can run it, debug it, and typically for debugging, you will have some facility in the target. Maybe you may be able to connect a serial port or something, or so that any printf that you do on the target, right? You use a printf, it may come on serial console. Again, for the printf to work also, normally the embedded vendor will give you some simple libraries, just like the C libraries which are available for Windows, right? They may give you a simple set of libraries by which you can do simple printf type of thing so that you can debug, right? It's always good to get some messages so you know the code is running, it's doing what it is expected to do. So all that is done by a small library which is linked to your program so that you can use things like printf and all that. Because otherwise the code you write may be very small, but you will link the required functions from the standard library which is needed, generate the binary, push it to the target. And typically in an embedded system, you may not even link the entire C library. You'll only link probably what is needed, the absolute minimum that is needed, so that the code footprint is much smaller. So the library versions available for an embedded systems are also smaller footprint. When I say footprint, the amount of memory needed is much smaller, and that is pushed into the target. The code runs, and then if you see an error, you kind of come back here, edit the program. So the cycle continues. Okay, it's an iterative process. The main difference is you have to understand in the embedded system, it's a cross compilation typically. So you compile for a target. The linker is important to understand. So you go and link all the different addresses as needed by the target environment. So that is when embedded system program has to understand the hardware, the architecture, address map, and things like that. Then you download it, push it through the hardware interfaces available, run the code, use the debugging facility which are available. And some of the good development environments also give you ability to things like step through the code, right? Normally when you debug, you let the program run, you may not know where the error is. So you may want to step through line by line at a C level or at an assembly level. So typically good debugging environments are also available in the IDEs. So they again work with the target hardware support. Normally, most of the ARM-based processors provide good support for this debug. There are some standard interfaces which have been provided called core site. Many things are there. So using that, the IDE will be able to step through the code also. So you can actually step through the code and see what's happening. And then finally, once it's all done, then you will go to the next step of, releasing the code to the public or, until the product is ready, then you may go and flash it permanently or whatever. When you want to do volume manufacturing, probably at the manufacturing stage itself, once you're completely tested, debug, your binary is available. That sometimes will be sent to the factory where the manufacturing is happening. So they will automatically flash it when the system is getting produced itself. So when it is shipped to the user, system is ready to, because the user is not going to use IDE toolchain and all that. There's only development time. Once the development is done, you will probably put it into the flash at a manufacturing stage itself, and then it is shipped to the user. Once the user starts up, things will run automatically. Okay. So here we are just these are some of the popular tool chains for ARM. Keel is one. There's something called IAR. There are many more. People use in Linux, they may even just do GCC with all the linker support that is needed. So as I said, right, these all support good way to debug the code running on the target. And most microcontrollers provide an interface by which you can get that support enabled actually. So modern microcontrollers, microprocessors give you good support for debugging. And many tool chains also allow the way to flash the program. You can either push it into RAM if RAM is sufficiently available, or the tool chains will give you a way to flash it into the device. Because there, as I said, there's a small component which is there, which the microcontroller vendor has given. It's called the boot ROM, or there could be other interfaces on the board through which you can flash to the board. Flash programming, there is a method by which you can program a flash. There is some sector by sector you have to select and write to that. And as I said, right, software development, generally we don't have to start completely from scratch, right? We saw that RA chip from Renesas. So they give you a good amount of initialization, configuration code, simple peripherals. So they give what is called as, in Renesas case, they call it FSP, flexible software package. So for pretty much every peripheral, they're given all the basic initialization code, configuration code. So there is a lot of support available. So you don't, as an embedded programmer, you don't need to completely start from scratch, like read the manual and start writing. There is good amount of reference code available which you can use, so that it is faster. It is also less error prone because the code has been tested by the microprocessor vendor or the microcontroller vendor to work. So when you use it, you already are starting with a good base to start actually development much faster. So some of them even provide user interface. Like when I say user interface, we saw that RA processor, it has so many peripherals, clocks, and all that. Some of the tool chains, Renesas has a tool chain called E Square Studio. They call it E Square Studio, which is actually a plugin based on Renesas. They have that. So if you go to some of the initial screens, they show you all the hardware blocks available on the chip and allow you to select what is needed, what you're going to use. So once you select, it automatically generates some configuration files, which allows the initialization of the chip to be smooth. Like basically unnecessary peripherals are turned off and stuff like that. So they give you a screen where you can go and configure what you're going to use, and that minimizes the amount of manual effort that you have to put in. So good thing is nowadays all the semiconductor vendors give you good amount of software support, which really allows you to do embedded development quickly. So depending on the platform, you will choose whichever is the right tool chain. So I just mentioned a couple of things like Keel and others, but there are many more based on the chip vendor. They may give you their own support. Okay, so basically that's really the talk about IDE. You'll have a later session where there will be a walkthrough of a typical IDE, where we will do a screen sharing and we will show you how to take a simple program, go through the steps and run it on the target, right? So that whatever we just saw as a theory, you will see it in practice, how to do the development using a real IDE. That will be a separate session. So all you have to understand is important things to remember, to summarize and to make sure the key points are understood. The important thing to understand in embedded, it's mostly a cross compilation environment. You have to understand the hardware, you have to understand the address map to set up the link map properly so that the code is generated for the right addresses where the code is going to run. And there is good amount of tools to support debugging through the JTAG or other type of probes that are there. And there's also the tools also allow you to download the code into Flash directly or into RAM based on the situation that you're in. And then there are a variety of IDEs, so you choose what is appropriate for your needs actually. Some are paid, some are free. So there are a variety of things which are available. So ultimately, again, not some IDE vendor may support only some process. So you have to choose the IDE which is based on the processor that you have chosen for you, or the microcontroller that you have chosen. So if you're choosing RISC-V, you have to then find the IDE which supports RISC-V and so on actually. Okay.